Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
Hello, and welcome everybody.
Welcome. Another episode of Ask Us Anything about electrochemistry. Slightly different setup. I'm working from home today.
You gave it, I was saying we're live from discrete locations around the world, and we won't give it away except you just said you're at home, so now it's over. Everyone knows where you are.
Yeah. Everybody knows the choppers are coming on me right now.
That's right. Yes.
All right. Well, first off, I guess before we begin, thank you for those of you who stopped by the Pine Research booth at the ACS meeting in San Diego earlier this week. It was nice meeting a lot of you. I have some pictures. I think we'll post them later on social media, but always great to see some fans. And then I guess with that said, we can just get right into the first question. There were a few questions that we received. Paul Mining, we do see your list of questions. We will get to them in a minute, but Nora had a question earlier. She asked, why in a constant potential electrolysis experiment of the electrocatalyst choose a specific potential? So this question needs a little bit of wording or perhaps clarification, and I know that Nora also mentioned this question on the chronoamperometry video on our YouTube channel. So typically, so at constant potential electrolysis, you're stepping the potential of in your electrochemical system to some type of potential where ideally you are oxidizing or reducing your catalyst and having a reaction occur. And so you need to choose a potential at with which that happens. So I'm going to just share my screen very quickly to just show you, generally speaking, what we're talking about or what happens. Am I sharing, Neil?
Yeah, you're good.
Okay.
You're good.
Just making sure.
We're not visible anymore, but I guess that's probably fine.
Oh yeah, that's okay.
I don't know if that. There we go. Now we're visible.
Yeah. So typically you pick a potential. So this is like you set the E to some value. Let's say it's 1 volt. So the applied potential, the applied signal, will look something like this. And this is also over time. There'll be nothing, and then at kind of t equals 0, you'll move to like 1 volt. Right? And during that experiment at the same time, your current will spike up, and then you will get some kind of slow decay. This is a chronoamperometry experiment. It's a constant potential experiment where we're holding the potential at plus 1 volt. Now, in a cyclic voltammogram, let's say this is the CV of your catalyst, and this is again potential, and this is this is potential. This is current. This is current, and then this is potential. You know that at different potentials, your catalyst has certain like levels of activity, sort of say, right? Your E naught is somewhere here, but you need to pick a potential that is sufficiently, let's say, positive or negative, such that this reaction has no problems occurring. So the selection of the potential that you use in a constant potential electrolysis experiment is based in some ways on the cyclic voltammogram. Which potential are you picking? And you need to pick a potential that is sufficiently over. Typically, you want it to be very much over the potential. You don't want it to be here. This would not be a good place to to do your experiment, because you're really at the onset potential of this. You could get a much faster rate of the reaction to occur if you picked either this one or especially this one. And at a certain point, applying a very high potential might actually be detrimental, as other processes can occur. So I know the question wasn't exactly worded like super well, but I think when it comes to choosing a potential to do chronoamperometry or constant potential electrolysis, you want to pick one based on the cyclic voltammogram, and pick one that's sufficiently positive or sufficiently negative if it's a reduction reaction, that there's nothing that limits this current spike and how much current you're getting. So hopefully that kind of answers the question, Nora. But if you have further questions or further details about your question that you would like covered, I'm happy to elaborate on it.
Very good. I'm glad you answered that question, because when I saw it, I saw CPE and assumed it meant constant phase element, because
Right.
my mind is always on impedance, and that is
Yes.
apparently not what the question was about. So very good you're here. If you weren't here, I would have been blabbing on about impedance for a while, and then it would have been like, this is not what I asked. Why are you here?
Well, it's not 100% clear if that was what she was asking,
Well,
but
most
based on the
probably it
context,
is,
I think
especially
it is.
in the context of like the chronoamperometry video you made or whatever. I just my mind is always on impedance. I can't help it. It's my thing. Or it's on batteries, which leads me to palm mining's question. You like that transition right there?
Yeah,
So,
that's right.
so palm mining has a couple of questions, and the first one here is: suppose we do GCD, galvanostatic charge discharge in capacitive material in the range of 0 to 1.5. After the discharge cycle, the charge will start exactly from 0. But if it was a battery material, after the discharge cycle, the charge starts from around 0.3 or 0.4, not exactly 0. Why does this occur? Um, so I think for the most part, the answer is somewhat of an intrinsic thing related to the materials that are used for supercapacitors versus batteries. Um, the other is it's actually an odd phenomenon that I've had some answers to at times, and then some brief, admittedly brief, I don't know, foray into the literature to try to understand it a little better has left me somewhat more confused, because it does appear, again, based on a somewhat brief, um, just look at some literature and explanations. It doesn't seem anybody is maybe perfectly certain as to the phenomenon when it comes to batteries, which is to say, like when you stop charging a battery or stop discharging a battery, the voltage relaxes and doesn't stay there. Like you can discharge a battery, and it's as a tangent, it's one of the reasons why, for instance, you charge up a battery with constant current with a GCD up to 4 volts or whatever the upper voltage is, right? Do is they hold it with a constant voltage, which is a chronoamperometry experiment as well, at 4 volts for a little bit after that, and wait till the current decays. And to me, it always the interpretation of that I always felt was accurate was that it's like topping off your gas tank. If you're filling up your car and you're pumping, you sort of add a little extra in there. So like holding the voltage at the upper limit, letting the current decay down is like topping off your battery, charging it up just a little bit more. But it's also indicative of this phenomena where if you charge a battery up to any voltage and then you release the current, the voltage will decay and drop a little bit. Now, I think I've heard it's a like an IR drop kind of a thing, because basically there are, even in a battery where there's less of it than in an aqueous system or something like that. There's less sort of like IR drop or ohmic resistance or whatever you might want to think about. And this term probably isn't the right term because there's no reference electrode. It's often a 2-electrode system. So the idea of IR drop is usually between working and reference electrodes. So pardon the use of this phrase. It might not be the right terminology to use in the context of a battery. But the point being that there are some amount of milliamps, microamps, gigaamps, whatever, as part of your charging or discharging process that are taken up by processes unrelated to the charging or the discharging, right? And so as a result of that, assume that they're in series. It's kind of like the total voltage is actually a series of other voltages. And so when you get to 4 volts or you get to 0 volts or you get somewhere, you're not actually at that voltage. You're actually somewhere else, because some of it's what IR drop is, right? On compensated resistance, what it is in some sense, it's parasitic. It's eating away at the actual voltage or current that you're trying to get, right? And so in a battery, that exists too. There's cabling or electrolyte resistance and things like that exist to some extent. And so I believe that's the most accurate perhaps explanation, other than just maybe just something intrinsic about the material and the way they operate. Like you could watch, for example, lithium in a battery or sodium ions, like they move into the one side or the other when you're charging or discharging, and then when you turn off the current, you turn off the power supply or whatever, they kind of start to they diffuse backwards or whatever. That's somewhat, I don't know, somewhat of a natural process, and that is what can lead to this sort of difference in 0.3 volts, 0.1 volts. The exact amount can vary. As it relates to a supercapacitor, though, or a capacitive material, though, a lot of those phenomena are not at play, and it's a fundamental difference in the mechanism of charge storage. A capacitor setting up with a double layer essentially, and then discharging and charging in that manner does not follow the same electrochemical principle and mechanism that I just described for a battery. And so for whatever reason, it's less affected by those kinds of things. And so I don't know, the voltages become more precise or something of that nature. Like I said, I think that, it's something that's a little, other than the way that I just tried to describe it, it's perhaps not perfectly well understood, why there's this kind of lag or delay in the voltage. And it's one of the reasons why, we're up again. When you charge really, really fast, you're likely to have that delta of the voltage or be bigger, because it's like you're charging it up so fast that when you hit your limit, it relaxes, perhaps intuitively, if you think about it, more. Whereas if you charge really slowly, really, really slowly, similarly to like doing a LSV or a CV, the slower that you scan, you're reducing background charging effects and things of that nature. And so the voltage is more accurate when you stop the charging or discharging, for that matter. So I hope that's like somewhat of an overview explanation of this. It is kind of an odd phenomena for sure with batteries. And I kind of tried to explain it to the best of, I guess, my knowledge there, but it is an interesting kind of observation for sure. And then the next question Paul Mining has is related to OER. So you've laid out basically the acidic and alkaline reactions for OER here. So the acidic reaction is 2 water molecules, gives you oxygen, 4 protons, 4 electrons. And then the reaction for alkaline media is 4 hydroxide ions, give you oxygen, 2 water molecules, and 4 electrons. Okay, and so you've said that reaction 2 is understandable, that it is in an alkaline media, as on the reactant side there is OH minus. But why reaction 1 is said to be an acidic medium, as H plus are not on the reactant side but are produced after the completion of the reaction. Reaction 1 is just happening in a neutral medium. Also in reaction 1, if we add H plus, it would drive the reaction backwards. My doubt is based on what reactions are said to be in acidic or alkaline media. So first of all, you're conflating a couple of concepts here. The idea of adding like protons would push the reaction the other way. That's what Le Chatelier's principle, and that's for an equilibrium reaction. That doesn't apply here necessarily. The reaction can be reversible or somewhat reversible, or you can, the opposite of this is the oxygen production reaction, for instance, going the other direction. But I don't believe that you can use the principle of like, if I add more of the reactants, it pushes it to the products, or vice versa. That's for like an equilibrium reaction. Again, I think Le Chatelier's principle is that right, Alex? Is that the right when you?
Yeah, it is.
Yeah. So that isn't applicable in this case. Is the point?
I mean, the way Palmani drew those reactions, he just made them one directional.
Yeah.
Like they're only one direction. There's not like it's irreversible in the way it's drawn, unless, as you said, the reactions are actually in equilibrium.
But I also think that these are all different concepts. So whether, well, I would suffice it to say, for instance, that an irreversible reaction is not going to be in equilibrium because it can only go one direction. But even a reversible reaction need not necessarily be at equilibrium. Like existing in a like Le Chatelier's principle is like you have a closed vessel or something, and you have like concentrations of like A product and B reactant or whatever, and you can drive the reaction one direction or the other by altering the product or the reactants or the temperature if heat, if it's exothermic or endothermic. That's sort of this. That's the principle. That's like Le Chatelier's principle, and how you can drive reactions one direction or another. That just doesn't apply in this particular situation. It's not. The oxygen evolution reaction, when you're performing it in this way, is not like when you're producing the oxygen, there isn't like an equilibrium at like that. That's not the situation that you have at the electrode surface, that there's like an equilibrium where it's going back and forth between oxygen and hydroxide molecules, or oxygen and protons. Like I don't think that's the case. Like I just don't think that's an applicable. I think that's the main, if I'm not wrong here, I think that's the main mix up, is that you're applying a chemistry like fundamental thing inappropriately in this context.
Is it just because like they're different phases? Like oxygen in this case is a gas.
Yeah, I don't know exactly because they're different phases, but again, I just think it's, you add an electrode, you have an applied potential, in this case a positively applied potential to drive the oxidation reaction. I don't know. You could do like
well, we know that the reaction changes the potential depending on the pH, right?
Right.
So if you're changing the proton concentration, you're making one side of the reaction like more or less favorable, or something.
Maybe
like
that's
that.
one way to put it. Maybe that's the. I was going to say, if you think of the Nernst equation and you think about the way pH changes. So okay, maybe that's a more precise answer. It's not that it drives the reaction backwards in the way that you might be imagining with Le Chatelier's principle. Like it's just going to produce more, I guess, if you're adding, what was it in context of adding more protons. So it's like adding protons will in theory just give you more water molecules or something like that. But the aggregate impact of adding more protons is making the solution more acidic, which means the pH is going down, which means that the standard potential for the reaction is going up. So again, this is where it's, to be precise, you're doing electrochemistry. So for the same applied potential, if the E0 is now moving up, you may not be producing as much. So you might be quote unquote driving the reaction the other way, but it's more like with respect to, like if you're at this reaction is 1.23 volts. That's the standard potential for the oxygen evolution reaction. So if you're at 1.3 volts, whatever, just make a potential, right? You're driving it in the oxidation pathway, like primarily to a certain extent. Okay. Now you make it more acidic, which means you are adding more protons, right, to your solution. You are therefore decreasing the pH and increasing the E0. You're increasing the E, the potential, not E0, you know what I mean? You're increasing the potential that it's going to occur. So let's say it goes from 1.23 to 1.4. Well, now you're at, and we're making the assumption you're applying the same potential. You're still applying for whatever reason. You have a vessel and you just like dumped a bunch of nitric acid in it. I don't know why you would do that, but that's what you're doing. Okay, great. So you're applying 1.3. Well, before 1.3 was higher than 1.2. So you're driving the oxidation. Now 1.3 is lower than 1.4 because the potential at which the reaction, the standard, potential of the reaction is now above your applied potential. And so, yeah, you're not going to be driving it in the oxidation pathway as much. But I just think that that kind of thing, like the extra variable here of like the applied potential matters. It's not as though, I mean, if it happens in the way that I'm describing it, like you just have a 3-electrode system and you're just like applying some potential and then inexplicably you add a bunch of acid to your system, changing the pH actively without adjusting your applied potential for the pH and the reference electrode you're using and all the things, and you just do that, then yeah, you'll change the potential at which the reaction occurs, and you might sort of quote unquote drive it the other way. But it's not quite in the same mindset as the Le Chatelier's principle that I think that you are referring to. I guess that's kind of my point. The applied potential, because like the reality is like when you're doing this at a more acidic potential, again, the standard potential at which the oxygen evolution occurs will change. And you just, if you want to do that reaction, you apply an appropriate potential based on what that potential is. That's what is done. Like you have to figure out what potential to apply with your potentiostat to do OER based on the reference electrode you have and based on the pH of the solution. Like this is just what all electrochemists do. You have to account for that. And so like the number you type into the computer of your potentiostat will be 0.7 or 1.9 or whatever the number is, but it's you know the basis of 1.23 versus NHE at, I guess, the neutral pH, or maybe I don't know if that, maybe that's at pH 1, whatever that is, will change based on your H plus concentration. But you know, driving the reaction in one way or the other is only with respect to what applied potential you have. I hope that kind of makes sense. I know it's a little complicated, but that was my impression of your question, is that you're sort of conflating Le Chatelier's principle in a way where it's not exactly what you're maybe envisioning for what you might have learned about like a pure chemical, I don't know, chemical reaction or something like that.
Yeah, I think it's also the degree and perhaps the magnitude, but like, you know, he has the equation. I'm just like, if you write it out, you'll find that like, yeah, you'll drive the reaction one direction, but then you'll run out of some of the other things. Like you need O2, and maybe you run out of O2. You know, if you if it's whatever the limiting reagent is, also in some of these things too.
Yeah, if
So
there's no O2 there, then it's not at equilibrium anymore. It's not at, you
it's
can't
not gonna,
drive the
you're not gonna
reaction.
have that reaction.
Yeah.
So
The
so
other
yeah,
part of
and
this
then
question, I think I sort of glossed over it, but basically some of this is just like stoichiometry is the answer. Like why I think
yeah,
in acidic
you won't
media,
have
like you're sort of making a comparison between the two stoichiometric reactions. And because the hydroxide is on a reactant side for the alkaline one, you're sort of making the assumption that the protons should be on, you know, the reactant side as well. Perhaps naturally so, I suppose, because like, oh, well, protons and hydroxide are whatever. But I mean, first of all, if you just look at it the way you've written it as an oxidation reaction, like for charge balance, it's not physically possible for the H pluses to be on the left. You would need 8 electrons on the right if you had 4 protons on the, like, you have, it has to balance stoichiometrically. So on the alkaline reaction, there's 4 negative 4 charge on the left and negative 4 on the right. On the acidic one, there's 0 on the left and 0 on the right because there's 4 pluses and 4 minuses. So it's like just naturally try to write a stoichiometry reaction for the production of oxygen with protons on the left. Try to do it. I dare you. It's not it won't go well. So some of this is just sort of the natural consequence of stoichiometry here, I guess. And you know, why doesn't the alkaline one happen in acid media? Well, it could in theory. There's nothing, but there's just not a lot of prevalence of OH minus sticking around in acid media, which is to say there's basically none. I mean, there's technically some, but there's not a lot. So that's, I guess that's the answer. I don't know. You know, it's just kind of the stoichiometry of the reactions. If there's a lack of a better answer there, but
yeah. I guess when I read this question, I was thinking about like, so he's assuming that if you have a reactant, for something to be, so all reactions that we say are in acidic media have to have H plus in it. And to Neil's point, if it's alkaline, there's OH minus. There is no H plus in a basic system. And similarly, in an acidic system, there's no OH minus. There's only H plus. And whether it's on the reactants or the products, so you can even imagine the H plus is on the product side. So the system still has to be acidic, even if it's on the product side. Even if we're in, say, an equilibrium or a pseudo-equilibrium type of system, that reaction will not happen unless it's in an acidic media, because H plus is being generated. Because now you also have to note that these reactions, the OER reaction, is the sum. It's the finalized complete reaction. There's no like individual steps, right? We're not talking about like, well, oh, there's H plus and then there's an OH and then it forms water or something like that. These are the finalized reactions. They're not elementary steps. I think that's what we're really trying to get at, is because you end in an acidic medium and you have H plus, because it's the finalized step, there is no OH minus. So that's another thing about these reactions, is that they're not the elementary step. They are the final reaction for the entire process, if that makes sense.
Nothing makes any sense.
Yeah, especially in electrochemistry. So I hope that makes sense, Paul Mining. If we described it, if there's something that we didn't clarify, just
please ask us if you need any clarification. But it looks like Nora has a follow. I'm not sure if this is the same question you just answered, or it seems kind of maybe a similar question here, saying in CPE experiment for electrocatalysis, why do we need to apply 200 millivolts away from the reduction potential? Well, this is a specific one related to the irreversibility, probably. I guess, I don't know.
So when you say away from the reduction potential,
I assume less than.
I'm assuming you mean more negative of the reduction potential, and that can be. It can sound. I think one thing that might be very helpful is to recognize exactly what a reduction potential is in the context of doing of an electrochemistry experiment. So one thing that you notice in all, hopefully I'm sharing, that's showing up fine.
Yes, you are sharing.
Right. So in a cyclic voltammogram, right, you're doing a reduction, right? So let's do this the other way. I'm using the IUPAC method. So we have our reduction, and then we have our reversible oxidation. Sorry, I can't draw very well, but this is, yeah, okay. All right, so, and we know that we have, let's just call this E naught. This is the reduction potential. And you're applying, let's say here, which is kind of 200 millivolts MV plus, the E naught, more negative of the E naught. So this is minus 200 millivolts. So your question is why are you an additional 200 millivolts more negative than the E naught? Isn't it the case that at the E naught, that's the reduction potential, we should just apply that? Well, one thing to note in CV and cyclic voltammetry and just in electrochemistry in general, you'll notice that you actually don't get the peak current at the E naught. So that's just one observation. Hey, you can get more current at an even more negative potential. But the reason why we think of this E naught in the same way that we may think of, if it's more positive or more negative, you're not going to have the reaction. It must be at the E naught. We think that it's quantized, but that's not the case. The reality is something a little bit more like this, where you have what's a little bit more known as a DOS, distribution of states. So you notice you do get current over here, right? You get current over here. That's more positive, or not negative enough of the E naught, and that's because there is an area. There's a distribution of states, where it is sufficiently, and maybe I should just describe this as like an energy level. So we're talking about energy here, and we're talking about molecules and the different states that they're in. And so there are some molecules that are, hey, if the potential is here, you can get a redox reaction to occur. And the E naught is kind of around the peak. It's kind of around this center of the distribution of states. And this is because you have a molecule in solution. So the reason why we pick like 200 is because, well, we want the entire distribution of states. We want to make sure every single molecule can very easily get reduced for an electrocatalysis experiment. If we pick the E naught that's here, we may only get access to half of the available molecules. We're limiting, we're limiting ourselves kinetically. So that's one reason. Another thing is you may have an IR drop. When you have a very large area electrode for catalysis, and I'm just kind of making up. Maybe you have some big mesh, something like that. Maybe you're in a non-aqueous solvent. You're going to have an IR drop. You're going to have, the current that you pass times the resistance is going to lead to a decrease in the applied potential that you're doing to your system for electrocatalysis. So you need to overcome that IR drop. That's another thing that you want to do. So those are kind of the reasons, the things that you need to think about when it's like, well, why do we pick a potential beyond the E naught? What does the E naught actually represent? Well, it's kind of in the middle of this distribution of states, sort of say, or maybe it's a little bit more positive. But for catalysis, you want this reaction to go pretty quickly without generating or doing some other chemistry. So you're going to pick something more negative of the E naught to drive that reaction forward. So hopefully that makes
Let me
more
kind
sense.
of that's a good like fundamental answer as well, or in general. Let me also just explain it in the context of the Butler-Volmer equation, if I can, because
Yeah,
one
that's fair.
answer as well. Make sure that I'm sharing as well. If you,
Yes, yeah.
so the other which you put 200 millivolts, which is like a possibility, I suppose. One of the common, should we say, bits of electrochemistry consciousness is that not 200, but for, I'll just put N because I can't write the eta at the moment. 120 millivolts. So for an overpotential of at least 120 millivolts, this is commonly what we know as to drive the reaction in one direction so as to be virtually irreversible. And I'll show you why I'll do the calculation. So it comes to the Butler-Volmer equation. And so it's sort of assuming the kinetics of the reaction, but effectively this is the Butler-Volmer equation, describes how the current I is a function of, forget about I0 for a second. These terms are what matter. So this is the current effectively of one direction, and this is the current of the other direction, because alpha is the symmetry factor. So it's describing whether the current will be positive, in most cases oxidation, or negative, in most cases reduction. And eta here, which again I just put N for simplicity, is the overpotential. So in your case, why would you choose 200? Well, let's take a look at why is 120 the example, I guess you'd say, right? Let me keep this on the screen so you can see it at the same time. I just have an Excel sheet with some simple calculations here to kind of drive it home. So this is alpha. I know I just populated these boxes. I didn't label them, but hopefully you get the point. Alpha 0.5 usually, N is 1. Faraday's constant is 96.485. Our ideal gas constant R is 8.314. Temperature is 298. Now, what happens if, for instance, this right here is eta? This is the overpotential right here, zero, where I put a 0. So if there's 0 over, I'm right at E0. As Alex mentioned, this is where your density of states is like equally distributed between the oxidation and the reduction, right? What I've done here is just type in the exponential for both of these here, both directions. And according to the Butler-Volmer equation, technically speaking, they're exactly equal. So this is like the density of state. It's like exactly 50-50 current like possibility. I mean, you can see that very easily. E to the 0 is 1. So the reality is that I'm at the exchange current density or exchange current for both reactions. I'm equally split. Now, what happens when this is 120 millivolts, right? And why is that number valid? It's because it's about 99.1. That's the reason. So what we have, if we at 120 millivolts of overpotential, it means that I have roughly 99% of the current going for one side of the reaction and then 1% or less going in the other. And that's like the sweet spot. I think it's technically like 118 is the exactly 1%. Yeah. So, but we usually just do 120 for simplicity. And in your case, again, it'd be technically, I guess, the reduction. So it's this one is the one, but you can see it's obviously, it doesn't matter which side we have here. But basically, by that further sort of furthering this idea, if we go to 0.2 or 200 millivolts over potential, it's just further driving the reaction in one direction irreversibly. So now, you can this is what allows you to say, if like with some degree of confidence, all the current is for the reduction, reaction, 99.96% of the current compared to 0.04% technically is going in the other direction, but it's so minimal that it's basically like you can ignore it. And so 200 millivolts is just like overkill, but it's enough to probably like effectively drive the reaction, really far in that direction. Just mimicking what Alex talked about the density of states on a more of a theoretical or fundamental level. But mathematically, that's kind of the other way to look at it is through the Butler-Volmer equation, I guess. So just thought I'd kind of add that in there. Mathematically, I haven't showed that one very often. I show the Butler-Volmer equation a lot, and we talk about TAFL. Ask us anything about TAFL every week. But that's one of the reasons, effectively, where that 120 number comes from. It needs to be irreversible and makes all the current basically go in one direction. So.
Nice. Yeah, that's correct. It looks like we have a question from LinkedIn, which is always nice. Tharun is asking, how come the voltage is applied in PEM fuel cells practically?
Do you mean like how the voltage is applied practically, or you're saying how come? Are you asking why voltage is applied at all, or how is it like? How do you practically
apply voltage? Yeah, because like, isn't it a fuel cell? So the voltage is just based on the difference between the anode and the cathode, and you're pumping a fuel through it, and that creates a voltage difference.
Yeah, it's related back to the oxygen evolution reaction we just talked about. It's actually exactly that. So the standard potential is actually opposite of what the person Pam Palmiting was showing earlier for the oxygen evolution reaction. So it's actually 1.23 volts for a PEM fuel cell is the reduction reaction, the oxygen reduction reaction potential at the cathode, and the cell potential or voltage of a fuel cell is cathode minus anode, and the anode is just the hydrogen evolution reaction, which is 0. So the voltage of a fuel cell, the theoretical obtainable voltage, is 1.23 volts, basically. There are a number of ways in which a fuel cell is interrogated and used. Sometimes potentiostatically, sometimes galvanostatically. But I think, Tharun, if you can clarify, what are you asking? Like, how do I get a polarization curve? How do I get a power curve? I please clarify. I don't know exactly what you mean when you ask about voltages with a PEM fuel cell. If you can clarify your question just a little bit, I might be able to kind of give you a more informed response, I guess. I don't entirely know what you mean. I do have some experience with fuel cells, PEM fuel cells, and polarization curves and things of that nature, but I don't really know what you mean. So please clarify if you can. I can show you, for instance, how a polarization curve is sometimes acquired. I could do that, or how to calculate a power curve or something like that. But yeah, I'll sort of wait. We'll answer another question, I think, in the meantime. And until then, please feel free to clarify what it is that you mean, and we'll keep an eye on the chat. Until then, I think this was a question. Was this from last week or a couple weeks ago? I think I'm not exactly sure. But Grace had asked a question. Can you explain about kinetic charge storage mechanism? And the word kinetic is kind of throwing this question for a loop a little bit, to be honest. I don't know what you mean by kinetic. Like, kinetics is the speed of a reaction, but it just sounds like you're asking about the charge storage mechanism.
Or maybe you're referring to like a Faradaic charge storage
Yeah,
mechanism as opposed to like a capacitive charge storage mechanism.
perhaps
Maybe we're
perhaps
not so
that's.
sure.
I'm not entirely sure.
So
My assumption is you're sort of asking just like, how does a charge storage mechanism work? And so I can kind of describe that for a battery. It's, again, sort of my, I don't know, most well-known topic here, I guess. But like, for example, for a battery, there's a few different ways in which the charge storage occurs. There's three main mechanisms, basically. There's intercalation, there's conversion, and there's alloying. Intercalation is probably the most common because it typically happens with carbon. But basically what you have is a battery. So you have an anode, you have a membrane or a separator, and then you have cathode. Okay. And basically the charging of the battery involves, this is for like lithium ion. Okay. So we have a membrane, we have a separator, we have lithium. Is my thing about to crash? It's about to crash. Oh, it's good. Never mind. Okay. That was good. We have lithium ion. It just like wigged out for a second. Okay. So we have like lithium ions all around, right? Hanging out in solution, going through the membrane, being really happy. And we have an anode here. I shouldn't draw it green because it's graphite. Graphite's black, but too late. It's green. No, it's not too late. I lied. I'm making it this color, like for carbon. So the anode is usually carbon, graphite of some kind, and the cathode is just some transitional material. Okay, and so the charging mechanism is effectively when the lithium ions go in this direction. This is charging. Charge. And so the again, probably most common charge storage mechanism is called intercalation. Okay, and it's basically just where the lithium ions intercalate or join into the microstructure of the anode material or the cathode material, but in this case, the anode material. And so effectively what we have is the reaction is often written something like, it's actually like C6 or six carbons. You'll see it written sometimes like this: 6 carbons plus X lithium plus X electrons is in, it goes back and forth between LiC6. Okay, and so the C6 is because I think it's like the carbon's sp2 hybridized, so it's in like a ring structure or something like that. I'm not an expert on the morphology precisely of all the different kinds of carbon or graphite or graphene or all these things, but in any case, this is basically the stoichiometry. And so this X is usually between 0 and 1, and that describes the percentage charge or discharge, like 100% charge, 100% discharge. So X is 0.5, it's 50% charged. And it just describes that the lithium ions are quite literally, and I've seen microscopy where they show this. They literally intercalate. They like penetrate into the anode, and I suppose, again, microscopically, I'm not an expert in this, so pardon me if some of this isn't like the best. You have all these carbon rings, and it's like you can just imagine the lithium kind of entering into the lattice somehow. I don't know precisely how. I don't know is it right in the middle, or does it like, come out of here on the side? Like, I don't know precisely, but it's something of that nature, and it just and that we call that intercalation. So with apologies on the probably some errors on the morphological or elemental here drawing changes. It's something like this. So that's the first kind of charge storage mechanism. The other two, alloying and conversion. Conversion is just a chemical reaction. So something like nickel oxide, for instance, works as an anode material as well. And the reaction for nickel oxide, I'm going to have to figure out the stoichiometry in a second here. It might be 2. I got to write it and then I'll figure it out. There's Li2O, so I think there's 2 Lis, 2 electrons plus nickel. So we call this a conversion reaction. Okay, and there's similar conversion reactions for things like, I think, cobalt and other things like that. So this is a charge storage mechanism where lithium is, and it will go back and forth, but it's like actually a chemical, it's a full chemical like reaction. Like nickel is changing from nickel oxide to elemental nickel. Nickel is being, reduced from 2 plus to 0, right? And in the process, and we're forming this lithium oxide in the process, or so this is what's called the conversion reaction, and this is just another mechanism for the charge storage. So the lithium ions and electrons are deposited, I guess, on the anode, and it converts the nickel oxide into nickel in this case, and then you convert it back when it discharges. The last one is alloying. I think here's where, to be perfectly honest, I don't know very well how to explain, if I'm capable of explaining technically, the difference between alloying and intercalation. In my mind, they're pretty similar. I suppose we call it alloying when there's something kind of like how we call something that mixes with mercury an amalgamation. But when we mix other metals, we don't call it an amalgam. It's like a specific word for mercury. Alloying, to me, I guess, I think we call like tin or silicon when there's, I don't know the reactions well enough off the top of my head, but silicon or tin plus lithium plus electrons. There's some charge mechanisms that happen there, and I think those are alloying because it makes like, especially like sulfur, tin, some of these things they make like, Li2 SN5, like there's some weird complexes that occur, or some weird alloys that occur. And anyway, I don't know 100% the distinguishing characteristics that differentiate alloying from intercalation or what have you. But that is the third classification, at least for like the charge storage mechanism for a battery. So I'll leave it there because, again, I don't know that I can speak with more clarity about it than that. But that's those are the different kinds of mechanisms that exist for all sorts of different materials. And as a battery researcher, for instance, when you're finding a material to study or use, it is usually your job, or at least it's relevant to consider what kind of mechanism does your material do when it undergoes charge storage. Is it which one of those three is it? And yeah, there's a broad variety of materials, some that do some of those and some that do others. I once, when I was in graduate school, made a chart of the periodic table of which does which, and I don't remember it off the top of my head because it was a really long time ago and I'm old. But in any case, so that's hopefully a brief overview of charge storage mechanisms and I don't know how they work. So,
all right, very good. Looks like we have a new question that came in. Hamutha is asking, probably butchered the name, but pronunciation, but it's asking, how can we systematically determine which electrochemical reaction or process corresponds to each peak in a Bode plot or each semicircle in a Nyquist plot when analyzing impedance spectra? And I don't know if he looks like it ends on an I, so maybe there's another part
yeah, if there's
to
a
this,
follow-up,
but
you can keep following up. Yeah.
but generally speaking, I think every single electrochemical system or reaction is different and unique, and there are some known things about interpretation of Nyquist plots and Bode plots when it comes to understanding a certain electrochemical reaction. But EIS sometimes by itself, I have found it isn't enough. It's a very useful tool when trying to get useful information about the capacitance, the charge transfer resistance, solution resistance, for example. Also, whether you're in a 2-electrode configuration or a 3-electrode configuration will also determine, how you interpret those semicircles in the Nyquist plot. But there are some general things that we know on a semicircle typically represents an art kind of a void element, a resistance, and a capacitor in parallel. That usually refers to an interface. We know that the Warburg impedance has a kind of a 45-degree diagonal line. If you have multiple RC time constants, if you will, that can correspond to multiple interfaces that are at play. So it depends a lot on what the Nyquist plot is. I don't think that there is a systematic way of determining an electrochemical reaction just by looking at the Nyquist plot alone. It depends a lot on other chemistries and what you may know about the system and about assigning in order to assign a specific semicircle, if you will, to a particular process and what that means.
And really what it boils down to is if you know those things that Alex just said, you know what the processes are, hopefully based on other calculations or just sort of knowledge other than the EIS, you can know whether they're fast or slow, something like that. Because it's not a systematic way to assign things per se in general, but very broadly speaking, the semicircles that appear first are fastest. The semicircles that appear later are slower. The semicircles that appear often, it's not exactly always given, but most of the time that's the case, because the processes that occur slower appear at lower frequencies, generally speaking. And so the faster, often less resistive processes will occur at higher frequencies, which is on the left side of the Nyquist plot. So sometimes the way you can do this is you can say, well, I have these 2 or 3 or whatever, like reactions occurring, in my system or something. I know this particular one is really, really fast, and there's not a lot of issues with it. It happens so fast. I'm at a good potential for it, whatever. And you have 3 semicircles. Well, maybe you could say just an educated guess at like the first of your semicircles is that process. Like that might be something you can do. But again, it does require a lot more knowledge of stuff, for instance. Like, okay, yeah, the lowest frequency is diffusional effects take, and those are slow. So there's some things that you can draw the conclusion of, but just as a general rule, it's not like, well, at 17 kilohertz to 112 hertz is exactly always where the Faradaic reaction of interest occurs. Like, that's just not how it works precisely. It's not always that easy. You do need to have some other auxiliary information about your system.
Okay. All right. So there's we can go through some of the questions that we've never gotten to.
I know this is an opportunity to do that.
Yeah, while we wait for some new questions.
Yeah, exactly. So if we have any clarification about the PEM fuel cell question, we'll keep looking for that. But for now, we do have questions we've been trying to get to forever. So
yeah. So Meliodas is just asking, can you tell about differential pulse voltammetry technique and how it is useful in electrochemical experiments? So let's get to this one. Meliodas asked this a while ago. We never got to it. I will just talk a little bit about it. How what is differential pulse voltammetry? Why is my laptop working? There we go. So differential pulse voltammetry is again another form of voltammetry where we apply a potential and we measure a current. And typically, a differential pulse voltammogram has this, kind of the following form, where we have these pulses, and we continuously, pulse and then wait, and then we, so we pulse the potential up to some value. So this is potential on the x-axis, and this is time on the y-axis.
Other way around.
Sorry, the x-axis is time. The potential axis is the y-axis here. And so we start at some potential, we pulse it, we hold it for a given amount, a small, short period of time. And what we end up measuring is we collect the current at various points during the differential pulse, and we actually collect a difference current. And I forgot exactly which order it is. I believe it's something like, if this is I1 and this is I2, we're always going to do I1 minus I2.
That's correct.
Okay, so this is the current that's reported. So this is the measured one. So what we're looking at here is a difference in current. And there's some advantages in this type of technique. Your question was about like, well, how do you, what do you use this for? Why is this helpful? Well, it allows you to remove two kinds of background currents that commonly, can be plagues or can be problematic in electrochemistry. So it removes capacitive current because of the time. Usually the time that this current is actually collected, the electrical double layer has sufficiently decayed. It's been charged already. So you're measuring a current difference that has capacitance effectively removed. So capacitive current is removed. So current. Okay, so that's gone. And then we also remove background Faradaic processes, which are somewhat less common, but I don't call this Faradaic, but they're also removed. Okay, so you also, I'll use red this time. We also remove background Faradaic processes. And the reason why is because let's say that there's some process that's happening here, right? So some process is happening at this potential, and it's always there. It's kind of in the background. Well, you're subtracting a current where the current associated with this background process at I1 is the same as the background current at I2. So when you subtract those two currents, the background Faradaic process goes away. The only Faradaic current that you measure is the Faradaic current that is associated with changing the potential from here and here. And so that is the current that you actually measure. And ideally, you have some kind of E naught where you're scanning across this range, and this difference is what you're able to get. So those are the main advantages of differential pulse voltammetry, and you end up getting this kind of the resulting current, or the resulting graphs that you get tend to be these kind of single points, and then you end up getting very nice, well-defined peaks that really only contain signal associated with the molecule of interest that you're looking at. So it's a very highly sensitive technique when it comes to, and again, it's current versus voltage. And that's kind of the advantage. It's actually used in a lot of analytical techniques where you have a very low concentration of a species, and you need to remove these background signals that commonly convolute your signal. So that's kind of a brief description, if you will, of differential pulse voltammetry in a nutshell.
Very good.
That's good. Okay.
So there's a couple of questions.
Yeah. Mm-hmm.
Live. So Mohammed has said, "Hi, I'm working on vanadium pentoxide based glucose electrochemical glucose sensor. Why am I getting an inverse relationship with current and glucose concentration, unlike the existing reports?" Excuse me.
Inverse relationship.
So I mean, it sounds like let's just say you create a solution with glucose and you have a sensor and you increase glucose. You want to see, I guess, an increase in current, but you're getting the opposite, decrease in current, perhaps, or something like that. I mean, So in general, we can't really answer this question with great specificity without. There's like 1,000 follow-up questions that we would need to have answers to.
Yeah.
Like, I need to know about your setup. I need to know about what precisely you're using, what your experimental setup is. We'd probably need to see some of the data. I know this is tricky. It's not. You're probably hoping for a quick answer, and it's a little hard to know exactly what's. I just don't have any of the context about your, um, you know, your experimental setup, your experimental design, all the variables of your experiment. Without kind of knowing any of those, it's really hard to know. But all I can kind of think to say as a general advice is actually sort of to piggyback what Alex just talked about. It's like, make sure that, things like the background current and capacitive effects and other things for somehow, which can really get in the way of those kinds of measurements, are not severely impacting your measurements. You might have a situation where, like, there's all these follow-up questions I would need to know, like, whatever the applied potential is, whatever the current is, what's the reaction you're trying to study, what's the electrolyte concentration, what does your physical electrode look like and setup, are the leads connected right, or all these things. But like, if you have a lot of like IR drop in your system and you're trying to get like a clean set of like calibration curves or something, well, you might be fighting against internal things in your system that are reducing the ability to measure the current of interest for it. So something like that. Those are some of the things that can really impact these types of measurements. And then, what kind of electrochemistry you're doing? Are you just doing like controlled potential, controlled current, or maybe a pulse technique would be useful if you're looking for a peak, or however the detection works. If it's just a straight voltammogram or a set potential, and then you measure the decayed current after a while. Like, there's a lot of follow-up questions here I have, but those are just a few things I can kind of think of. I don't know if you want to say anything about it, Ian.
Yeah, I agree that there are a lot of variables. Sometimes, this may sound strange, but like, if you're getting a reverse relationship, sometimes that means there's like a negative sign somewhere in your
That could be it.
system that's like, like just following you around, and it's like, because ideally, if you have a glucose sensor, and when you have more glucose, you should get more current. But hey, if there's a negative sign somewhere in your analysis, it's giving you a negative slope, and it's like,
Yeah.
why am I getting the exact inverse relationship?
Or it could be something as silly as whatever report or paper you're looking at is using the different convention, like
Yeah, that's right.
IUPAC versus the like Texas convention. So they might be showing more and more positive current, and you're showing more and more negative current. And those are the same thing, because in the Texas
Yeah,
convention, a positive sign on a current is a reduction, whereas the IUPAC
yeah,
version that most of us use, because it's the correct version, is the negative current is reduction. So like, you might say, oh, why is mine all negative numbers getting more negative and theirs is all positive getting more positive? Maybe you're actually getting exactly what you're supposed to get. It's just
yeah.
the convention. So yeah, that's a good point. It could be something silly as you actually are getting what you should get. Now, if the
Yeah.
signs are worked out and it's actually going in the
Mhm.
wrong direction, then it's probably something like I
Yeah.
described before. But yeah, if check that it's not just a simple chart or mathematical kind of
Mhm.
error there going on, that would be an easy explanation that you actually are getting the data you expect.
Yeah. Yeah, that's a
So
good
okay,
question. All right.
and
And
then
then we
Karthik
have
has a
another question
question.
from LinkedIn.
Yeah, from LinkedIn says, can you explain why it's preferred low scan rate than high scan rate in CV? It isn't, but it depends on the application and what you're studying. There isn't really a general preference or what would you say, recommendation as a general rule in electrochemistry to like do slower scan rate necessarily. It's not always the case. So just to be clear, maybe
Mhm.
with respect to the system that you're studying, you might have that be the case. Some of the reasons why you might scan slower is to reduce background effects. So um, the the peak, if you have a peak in your CV, and you have some capacitance those will be impacted by scan rate. So the capacitance will go up as the scan rate goes up. And so one of the ways to reduce the impact of capacitive effects is to scan really slowly. And by doing that, you can, in some cases, and I shudder to go down this road again, but you can more highlight kinetics and kinetic current apart from mass transport or capacitive or non-Faradaic effects by scanning really, really slowly. And so one of the things that people do sometimes is LSV at a really slow scan rate. Sometimes for corrosion experiments, they do something like this to isolate the hopefully kinetic current so you can make TOEFL plots. And so that's one reason to scan slowly, but it isn't as though you can't scan fast and get information. So the follow-up is whether it's due to movement of bulk, whether it's due movement of bulk to surface diffusion. Scanning slowly, you still would have diffusion. You're not going to not have diffusion. But
if it's anything, it makes it a little bit worse because you may have vibrations that'll affect your signal.
Yeah, like you like if you have a Faradaic like process, you're still like okay. So in the most extreme, I'll try to like I don't know, draw this in a way that might make sense. I guess like if you were to scan like 1 volt per second, like really really fast, and you get something like a really like wide gap. So this is like wide. This is like capacitive gap, right? And the peak will be, whatever, some large peak, and it's larger for fast scan rates. And then you scan slower. I'll just do the extreme. I'll do like 1 millivolt per second. So we go like 1,000 times less. Let's just say in a perfectly nice behaving reversible system, you might get something like this. Try to draw it. Shouldn't draw it that high. It shouldn't be that high, just for argument's sake here.
If you want to, we have software that does this. Like,
do we really?
Exactly.
I know. I should just
where like we can literally change the scan rate and change the capacitance.
It's true, but I'm already knee deep in this.
I know you're already like 90.
If you want to pull it up after, go right ahead. I know it's like I'm like halfway drawing. I'm like, oh yeah, we have software that simulates. Yeah. Isn't it better to watch me draw crooked lines? That's way better.
It's absolutely. I love that.
So scanning slowly. Let's just say a perfectly reversible thing. These peaks would line up. They'd still be in the same location, but they would be less. The slower scan rate, the peak would be smaller magnitude, which isn't good or bad. It just is. But you reduce this gap here. You reduce the capacitive gap. And in theory, if you scan really slowly, they would be almost the same on the way on both scans. But you can see, for instance, this peak still happens. So you still have a kinetic, increase in the current, and you still have like a decay. Like this decay is mass transport. Like you're not going to get away from mass transport just by scanning slowly. For instance, you're still going to have mass transport. You're just reducing the like capacitive buildup, basically. So anyway, yeah, if we want to talk about it further, we probably should just use our simulation software.
Yeah.
But I hope that picture looked really, really awesome.
It does. It does. Yeah. Well, let us know if you have any further questions about that. There's no. Some people sometimes like to go to very fast scan rates because they need to extract some kinetic information, and you have to sometimes go really, really fast to get kinetic information.
Yeah.
So
fast scan rates are good for probing faster things in some cases. So.
Yes.
Exactly. Yeah. If you scan too slowly, you'll miss it.
Yeah. Okay. Okay. So Nora is asking a question. Hi. Other than cyclic voltammetry, are there any methods that I could show my molecule is electrocatalytically active? Cyclic voltammetry it's really probably one of the best. It's very clear when you do cyclic voltammetry whether your system is electrocatalytically active or not. Just generally speaking, if I just show you, like when you have a regular cyclic voltammegram, like you just have to show, like, it's just two voltammograms. It's just like, okay, you have voltage, you have current. Like this is your CV under normal conditions. All right. And then when you like, and then it's like plus substrate, right? Whatever your thing is, catalyzing substrates. You know, your CV just looks like this. It's like, you know, it's just like, it's like super big. Or, you know, it doesn't go like that. Actually, it sometimes.
You know, we have a simulation software, right?
No, but the simulation software doesn't do catalysis.
I know, I'm just teasing. It's like I just drew all these things and then, you know,
all these things.
Yeah.
And
it
then,
doesn't do the
and
same.
then, and then you end up having something like this, where it's like, oh, you end up getting these weird like shaped voltammograms that look like this kind of like S-shaped looking voltammogram, with a huge current. Like these are homogeneous catalysts, mind you, but it's just very easy to show with and without the catalyst or the substrate. Your thing is electrocatalytically active for something, and it's easy to measure it too. You have current, you have direct rate information to showcase this kind of reaction. So this is especially for like homogeneous catalysts, but for heterogeneous catalysts, it's the same thing. You may even get a different onset potential. You know, it may start going up like this at a potential where that's shifted because your system's catalytic. So CV is really the best. There are very few systems that or electrochemistry techniques that you know, short of actually just doing the catalysis itself of like bulk electrolysis, and then you just measure how much like oxygen or hydrogen you measure with you know, GCMS or something. That's the best way to test whether your system is electrocatalytically active. So that's just off the top of my head. I don't know, Neil, if you know any other techniques for determining whether something's electrocatalytically active or not.
I think that is the best advice. It's sort of like not an answer, because yes, like other than CV, well, don't look other than CV, just do CV. Yeah, which it's true though. It just gives you a lay of the land. Like it just lets you know if anything is happening, and it's a quick way of doing it. Right? We joke a lot about how like pulse methods lost CV1. You know, like
Yeah.
in the world of
Square.
electrochemistry, like pulse methods are a good way to check as well. But like CV is easy to conceptualize. It's like start here, sweep to there, and then go back, and that's it.
Yeah.
And it just allows you to see in the most like quick and efficient way what happens to the current at all the possible voltages. Like that's it. That's like electrochemistry in a nutshell, right? I mean, we could say like do impedance at every voltage. You know, you could do some other stuff, and it's like a lot of those are a little more difficult to analyze or cumbersome or whatever, but it's like fundamentally, like to your point, like you have a substrate and you have a material. You're trying to see if your material is electrocatalytically active. Well, do CV on the substrate and then do CV on the substrate plus the material.
Mm-hmm.
And if it's electrocatalytically active, you should see a difference. And if it's not, you won't.
Yeah.
Like, there you go.
Yeah.
Right. It's like, it's very, very easy. And then comes the real fun of the analysis and the research and optimization and like figuring out how good it is, how bad it is, all that stuff. Right. But it's like, does it do anything? It's like, that's a very simple kind of an if then thing with CVs. I agree. I think it's probably the best way to go about it.
Yeah. All right. We got a series of questions.
Yes.
From
Tamogna has a few questions. So thanks for another wonderful session. Thanks for joining us. I have two questions. So I'd like to know if I'm trying to get LSV for a piece of, it's this question again, Alex. We still we haven't got to the bottom of it. I want you to know This is a question that Alex and I will eventually have a eureka moment, and we will like understand it fully, as
Yeah.
happens with us because of these live streams, because of you. There's a lot
Yeah.
of random electrochemistry topics. One of them is Mott Schottky for me, that like over the past year or 6 months, or I don't know, whatever, like I've understood to a certain level, and then all of a sudden it's like it just clicks and we just get it. You know, like even as in our professional, we're not in grad school anymore. So I'm just prefacing this that we'll try to explain this, and then in like some amount of months, we're going to understand it better. I promise. But
Yes.
basically, you're saying, yeah, I get for LSV for a piece of aluminum, and you find the E core and OCP are not the same, and they're 10 to 15 millivolts different. Is this wrong? You were expecting E core to be equal to OCP. So the short answer is no, you're not wrong. I do believe that it is not a necessity that E core is equal to OCP. So just a couple of things, and then Alex, I'll let you sort of take it from there. But like
Yeah.
one of them is that at OCP, definitionally, the current is zero. The net current is zero, right? Um, One of the things that I've been thinking about in terms of this, like why is E core not always equal to OCP, um, is that E core is coupled with I core, which I core is like I0 in the Butler-Volmer equation. It's kind of like the heterogeneous rate constant of the corrosion reaction you're studying of aluminum or whatever. And I core is not necessarily zero. And there's something about this to me that just sort of in my mind makes sense, that it's like, well, and I don't know, it's some of it's like whether OC, it's a net current. Net current being zero doesn't mean there's no current. It just means that the aggregate flow in both directions is zero. So there could, which is to say, at OCP, even at true OCP, is there no corrosion happening? Not necessarily, right? There could be oxidative current occurring. It's just that it's balanced by an equal amount of reduction current for whatever reason, whatever a reduction current. You could have 1 amp going this way and minus 1 amp going the other way, and that the net current is zero, but there's still a lot of current flowing for one thing or another. So that's just one part about that, thinking it through. But as a general thought, if you think about OCP where current is zero, well, I core isn't necessarily zero. In fact, it's probably not zero, right? I core is some number. So at E core, it probably ought not to be exactly OCP, because we have a definite like rate constant and corrosion current associated with that. So actually, I think that it we measure this as more of a thermodynamic kind of a set of quantities, E core and I core, when we take the Tafel slopes and we find the intersection, right? And we do it that way, and we're finding, in theory, a thermodynamic, or I guess a kinetic set of values for the corrosion current and potential. And they need not necessarily be the open circuit potential. But of course, generally speaking, when we are doing the actual electrochemistry experiment, we start around the open circuit potential, because when the net current is positive, we know there's an oxidation occurring, and that is the corrosion, generally speaking. So like from a practical perspective, when we're doing our corrosion experiment and we're inducing the corrosion, we start and move around OCP, because we know, for first of all, like what I said about the net current is true. So that means there might be some corrosion happening at OCP, even though the I is zero that the potentiostat is measuring, let's just say. But that just means we have no way to measure the amount of balancing current. We're measuring zero. So it's like practically, by polarizing slightly above OCP and getting a positive current, that's an oxidation reaction, which is like the corrosion reaction, we can like force ourselves to know that it's oxidizing, and we can study the corrosion, usually from like a polarization resistance kind of an experiment. So those are some of my thoughts, I guess, or some of the I don't know, thinking through the E core and OCP relationship. As I said, I feel like there's some more deep level of understanding, and it like eludes me still, and I'm trying to find precisely the way to rationalize through like what the real difference is between OCP and E core is, and like what E core really is, like very definitionally and precisely, because I do find there to be somewhat of a gap of knowledge here within myself, and maybe in general, but definitely within myself. So
Yeah, I was one answer that it's like, again, also need, like, I still need to think about it too, but one person described it as that OCP is at equilibrium and ECOR is not at equilibrium. It's like corrosion, even though it can be very, very, very slow, is not at equilibrium.
Right.
So the so that's why they're kind of definitionally considered like different things, so
Yeah.
to say.
Or if they're not different and they happenstance are the same or close to the same,
Yeah.
it's the net current thing is the answer. Like it's not at
Yeah.
equilibrium and there is some happening. It's just that there's some balancing current for some reason.
Yeah.
Like
Yeah. That's my
that,
thought
I think
about
that's
it.
the other I think that's the other part of it that I guess is like makes sense as an electrochemist, but it leads to the follow-up question, which again is like the gap in knowledge. It's like, okay, even if they are equal, what is that balancing current? Like why what reduction is occurring to balance and make the like OCP current zero? You know what I mean? Like what is it? Is it just electrolyte like something? What precisely is it?
Yeah, I guess that's
Like I don't
assuming
know.
that the OCP is a stable value and it's
Yeah,
not
of course. Like
changing.
if the OCP is moving all over the place, it's a whole different
Yeah,
situation. But yeah. So anyway, I don't know.
that's also true.
It's a lot. There's a lot of knowledge that I'm hoping will like enter to my brain sometime soon
Yeah.
about this because this is a good question. Just as the general point, I think. But hopefully, the quick answer, I guess, if you will, to Mugna is that I do not think it is in any way wrong that OCP and ECOR need be the same thing. I do not think that is necessarily the case. So I don't think you're doing anything wrong, is my point, at least in finding that conclusion. And then the second question here is that when we conduct a CV for platinum on carbon to get ECSA, I always see the oxidation of platinum and subsequent reduction of platinum oxide, but platinum oxidation peaks are broad and not well defined, where the platinum oxide reduction peak is always more prominent, sharp, and most like has more charge than the oxidation peak. So part of that, I think, might have to do with the fact that the platinum oxidation, the platinum reduction peak can also include the oxygen reduction reaction. Now, if you're purging with nitrogen or something and you don't have any oxygen in your solution, there might be a different explanation. But for instance, if you just like have like sulfuric acid and you do the platinum, for instance, let me share first. You do the sort of typical platinum CV in acidic media. It usually looks something like this. So you'll have usually 3 peaks here, give or take. And then you'll have this. Sometimes it kind of makes almost like a peak and then kind of goes down, something like that. It kind of varies. Sometimes you have this, it sort of slopes upward. Then when you come back, you'll usually have the reduction peak somewhere in here-ish. And then you have this, and then you have the platinum hydrogen kind of things. Okay, so basically this right here is like the platinum oxide oxidation. And this is where it does. It tends to be kind of broad. Sometimes there's a little bit of a peak like here, but a lot of times it's sort of broad, I guess, and sort of, and then you have, oxygen evolution reaction up here where the current will start to, if you let it go, it'll keep going up. And then this is the, platinum, basically oxidation reduction. And one of the reasons why I think you get, more, for example, more like charge in this than here is that this also is where you'll have oxygen reduction. So it's like if you just have, you're basically reducing the platinum oxides on the surface, I guess, whatever oxides have formed. I don't know if it's like PTO or PTO2. I don't actually know perfectly well exactly. I guess it's not hydroxides because it's an acid. This is something that's pretty well studied, and so my ignorance is only that I don't personally know perfectly well exactly what species are produced in these processes. But I do believe this is pretty well documented. So like in the literature, people will discuss different aspects of this. It's a very famous and popular and well-known CV curve or whatever. So people will have a lot of this process here and this process here are pretty well defined, understood. There's a lot of mechanisms that go with it. And so there might be an alternative answer or explanation that's like, well, this is like a 19-step process. Or actually, there's a lot of, whatever, for whatever reason, the amount of stuff that's reduced is there's more. But I think one of the answers is that if you have oxygen in your solution, you just have extra current from the ORR reaction. And that can be also what, so it's like in theory, of course, you should have the same amount of, whatever, over what range. You should have the same amount of charge, like the same amount of platinum oxide formed as reduced if it's perfectly reversible, right? Which I think it mostly is, or whatever. So if there's more current, it's like there's something else happening here on the reduction side. And one of those things that can happen if you have oxygen in your solution is just the oxygen reduction reaction. Platinum is very good at that. So especially if you reached into the oxygen evolution reaction up here, you could have produced a little bit of oxygen that's hanging out at the surface, and then that could account for that difference. And then also just in general, it's like where you pick, your limits to do this, and assume you're saying, oh, well, the charge is different. It's like, well, if I do this, it's, but what if it's out here? Like, where precisely are you, taking the limits to calculate that charge or whatever can make a difference just based on the same thing happens when you're getting the ECSA, because you're basically taking the platinum hydrogen adsorption desorption regions and getting this area. And I mean, if you've done this enough times, you probably even like these should be technically the same, because roughly the amount of hydrogen that you adsorb here should be the same that you desorb here, but it's not exactly the same. Why is that? Some of it's experimental error. Some of it's exactly how negative of a potential you pick. Is it here? Is it here? Is it here? That'll determine how much hydrogen is on the surface. The cleanliness of the platinum surface might have something to do with this as well, on both of these, for the platinum hydrogen and the platinum oxide, right? That the crystal facet of the platinum can make a difference, as well as how well polished it is and how clean it is. Because the platinum hydrogen regions, ideally you get sort of these 3 peaks, but sometimes it's like you only get 2. Sometimes it's broad and not well defined. And so some of those things might affect your measurement of the charge, like the condition of the platinum electrode itself. So I hope that kind of gives you some set of answers for why that might be the case. But those are just some of the general, I don't know, principles of that specific reaction, that CV there, and the kind of features that you see.
All right. Cigar is asking a question. In galvanostatic charge discharge test, within a potential window of 0 to -1, which cycle should I consider as the discharge cycle? 0 to -1 or -1 to 0? Thank you.
I'm not sure why you're going minus. I'm trying to think. I don't know of any.
Because to a certain degree, it's just a matter of switching the leads. Like that'll give you a minus. If
I
you
guess
measure it
I
that
wonder
way.
if do you have the leads backwards, because a normal charging and discharging system should probably have a positive voltage to it. So it's
And
hard
also,
for
I'm
me
assuming
to.
like you have positive and you have negative current in galvanostatic
Yeah,
charge discharge, right?
the
So
charging is the one. Okay, so the charging is the one that requires energy. In the context of a battery, for instance, or like a fuel cell, 3
oh, he
electrode
said he's
testing.
doing 3 electrode testing.
So what's the working
Okay.
electrode? Is it a cathode or an anode? Because that will determine the answer. If it's a 3 electrode testing, I mean, you're probably testing half of the system. But I mean, generally speaking, charging is where it requires energy, so it's not spontaneous. It requires you to put energy in. So discharging is a process that gives energy out, which means it's thermodynamically favored, and the again, we're in thinking about this of anode cathode kind of anode cathode terminology. The charging is where the anode is experiencing a reduction reaction. The discharging is where the anode is experiencing an oxidation reaction. Conversely, if you're studying a cathode, so working electrode is activated carbon. So activated carbon is probably an anode, but I don't know what system you're trying to study it with respect to. Like your charge, what is it? I guess I don't even know what you're trying to charge for specifically.
Yeah,
But
like what's going into the carbon.
yeah, like what's going into the carbon? What are you doing? Is it just as a capacitor or something like that? If it's a capacitor, it's actually, I guess it's like, it's a trickier analysis because, or it's a trickier way to think about it, because with a capacitor, it's like it doesn't matter whether you set up negative ions or positive ions at the surface, but like it's you're getting a capacitor. Like if you apply a negative, if you scan, like if you polarize negatively, you get like a capacitor, of like positively charged ions or something. And if you scan positively, it's the other way, but it's
It says I'm studying material for electrolytic capacitor. Okay.
electrolytic capacitor.
How much that helps.
Yeah, well, it's not the same as a battery. Obviously, it's a different.
Yeah.
I'm just trying to. I guess I don't know. I need to I want to think. Move to the next question. I might come back to this.
Oh, okay.
The idea of galvanostatic. I know people do this, and I guess it just kind of throws me a little, because the idea of galvanostatic charge discharge on a capacitor is funny to me, because it's like it doesn't take very long for a capacitor to set up, and it's like it does take a long time for a battery to fully charge or discharge. And galvanostatic charge discharge is like, I mean, it's quicker on a capacitor, like it takes place in less time, which is what capacitors are generally for. Like they deliver a lot of energy in a quicker time than like a battery can. A battery is more like, for longer term, slower sort of discharge. Like if you need a quick burst of energy or current quickly, a capacitor is a good choice. But it's like think about when you do a CV and you get the gap or whatever. It's like, this is why I'm thinking about it. Maybe you can think about it with me.
Oh,
Like
what do you mean the gap?
okay, so I do a CV in a non-Faradaic region, and I scan like 100 millivolts up and then 100 millivolts back or whatever. And it's like there's a positive current on the way up and there's a negative current on the way back. But it's like the capacitance is just like half of that current, and I is equal to Q is equal to C times the scan rate or whatever. And so that means I is equal to C times V. I is equal to
other way around. The current is
I
equal
is equal
to
to
the
C.
capacitance times the scan rate.
Oh, right.
Or the charge is equal to the capacitance times the voltage.
The voltage. Yeah, I had it backwards, right? So I is equal to C times the scan rate.
Yeah.
But like, which one's the charge and which one's the discharge? It's like that isn't part of this equation. That isn't part. It's like you're just getting the capacitance of the material. We're not considering which of those is charged and discharged. We're actually just looking at the capacitance of it.
Yeah, the voltage of the capacitor. So it is like, and again, this is also with respect to silver chloride as well, right? Because that's the reference electrode. So you're looking at the potential, and when you're at 0 with respect to silver chloride, the voltage of the double layer of the capacitor is 0 with respect to silver chloride. The voltage of the capacitor at -1 volts is equal to some amount of charge or some negative, or some negative potential. And so we charge it to that voltage if it's purely like, if we were just talking about pure electrical double layer capacitance, that's what we do. Like if we weren't even thinking about it as a battery, we charge the capacitor to a specific potential, and then it has that potential, and then it can discharge. If we all of a sudden stopped holding it at that potential, it would discharge or something. Um, so that's how I see it. And he wants to know whether or not you're calling one thing charge and the other thing discharge. If it's like 0 to 1 or 1 to 0, just like you would with a battery.
Yeah,
Um,
I guess I don't. I guess it's like there's similar things. There's similarities like with capacitors and batteries in terms of having like time potential curves as compared to like
mhm,
capacity potential curves that batteries have, for instance. But
mhm.
but it's like the I think that I think that um going up in voltage in general is the charge. If you have to like label one, like going from low in voltage to high in voltage, so I guess like -1 to 0 is a charge, and then going negatively from 0 to -1 would be the discharge, I guess. But that feels but that feels backwards to me only because my intuition tells me that a negative, but hmm, like
And I don't know what the electrolyte is or all that kind of stuff, but like you could say at the open circuit potential, you know, you could assume the open circuit potential of the system, quote, discharged is like around 0. So then you have to like, well, then you need to apply -1. So you charge the double layer to -1. And then if you then, disconnected it and then started measuring the OCP, it would just discharge to 0 or discharge to
would it
something
hold it?
else.
Wouldn't it hold its if you disconnect it and you charge it up, won't it
Oh,
stay
right.
there?
Yes. Yeah. If you
So it
yeah,
would
if you held it,
self-discharge, like in theory, I guess.
yeah, yeah. It would, let's see. The
Like,
question is,
okay,
would it slowly
so
discharge?
if this is an anode, is the carbon an anode in a supercapacitor, I guess? Because then it is the opposite. So then it's as you go, I think it's you would go more negative, it would be charging up because you'd be doing a reduction reaction as the current would
Mhm.
be negative, which would correspond to a reduction and a charging on the anode. And so then when you go from -1 to 0, you would be discharging. Um,
Yeah, that's one way to that's one way to look at it.
I think that's if the graphite is an anode, if it's not that specific, I don't know if I'm trying to like if if supercapacitors are like defined anode cathode. I don't know that they are necessarily, to be honest. Um, but it's when the what, I'm trying to wrap my head around this a little, and I just my reference is batteries, and there's similarities here, but it's not exactly the same, and so I'm trying to trying to get like a comparative kind of a thing here.
Yeah.
And that's the thing. CV is also usually used with capacitors to just get a direct measurement. CV or EIS is usually used to get a measurement of the capacitance, and then people plot capacitance, versus cycle versus time or whatever they do. Batteries, it's different. You're doing with capacity and these kinds of things.
Yeah, if you're looking for just positive charge, right? Like if
Mm.
positive current is the thing that defines, the voltage and things like that, then like, oh well, then you gotta go from -1 to 0 or something like that. But we always think about like negative voltage as the quote thermodynamically unfavorable thing. We have to add energy into the system to get it to do something. Um, But yeah, no, it's weird. It's definitely a lot of weird sign conventions that you got going on here, Cigar.
Yeah.
Especially
I'm
compared
just
to
looking
like
at a
battery
similar
level.
kind of a plot from a publication where they have that same similar window from 0 to -1. Um, and the way it looks is that let me take a look at the paper real quick, because I think it's a possibility of like where the 0 to -1, sorry, -1 to 0 is the charge. So it's the opposite of what I said. I know it's like, this is all very I don't know.
Strange.
Yeah, it's I'm pulling up the DOI at the moment of a paper that has a similar um plot, I guess. Just give me a moment. I'm just kind of looking at this,
Yeah.
see if I don't know that it's something. I don't know if I have I don't even have access to this paper, so that's a problem. So okay, so just like, I mean, I found, I was just sort of trying to find a comparison thing. I know it's tricky. I think why it's tricky is because like I just don't know um if the terminology is used the same way. It's much more obvious with a battery, I guess. With a supercapacitor, like this looks kind of like what you're referring to. And so I guess it's like from -1 to 0, based on what this looks like, that looks like the charge part of this. And then from 0 back down to -1 would be the discharge.
Mhm.
Um, just comparing it with what a battery sort of is like, when you go down to up and then up back to down, that's like charge, discharge. Um, but like, I just don't, uh, like with a supercapacitor, there's a capacitor material, like, um, it's not this, like there's the counter electrode could be anything. You're studying the capacitance on this material. It's a bit tricky here. It's almost like, is it an anode? Is there an anode cathode kind of a like situation here that's analogous um to a battery, or because I feel like supercapacitors, it's more like there's a material you're looking at as for a supercapacitor, not necessarily like in a battery. It's like there's the anode or the cathode, and with a supercapacitor, it's like you're just looking at one material, because that, I guess, is on both sides of a supercapacitor, maybe, or something like that. And so it's almost like charging and discharging, it feels almost like the wrong words to apply in some sense to it. Because like with a battery, there's the charging and discharging is clearly definitional of like intercalating on one side and deintercalating this. It's like whatever. But with a capacitor, it's like either the capacitance is there or it's not. And I don't know if this makes sense. I guess that when the capacitor itself is like you scan one direction, you have a negative, like you were saying, like negative.
You're building negative charge
Yeah.
on the
So there's like
metal.
negative charge, but so there's capacitance there, and then you go positive, and there's positive charge, and there's capacitance there.
Hmm.
It's like
Yeah.
it's just whether there's negative or positive charge, but there's capacitance all the same. So what differentiates charge and discharge? Like charge and discharge is whether there's buildup of charge or not. It doesn't really even specify if it's negative or positive. It doesn't almost matter in some sense. That's what's kind of throwing this, right? Like,
And the potential, you're measuring 0 to -1. That's all with respect to silver chloride.
yeah.
You know,
So that is
so,
arbitrary because there's a reference electrode there.
yeah, it's also arbitrary because it's
Yeah.
a reference electrode. You could
I think
very
that's the
well
point.
have.
Maybe that's the sticking point why I'm having a hard time answering, because if your current if your Q is equal to C times V. So if at your voltage if at a, it's like a negative voltage, you have a negative, you'll have a negative charge, which, like there's some negative amount of current over time or whatever, or it's a positive amount of current over time. Either way, that's current associated with like the buildup of the capacitor, right? Or something like that.
Yeah.
But either way, it's the capacity that's what you're studying for the supercapacitor material. It's like the the capacitor setting up is agnostic to whether it's positive or negative. That might be wrong, but that's what I'm understanding, is that it doesn't matter whether it's positive or negative. It's just setting up a capacitor on the surface. Whereas with a battery electrode, it very much matters whether it's positive or negative, because negative current or positive current means I'm putting in or taking out that's a very clear defined charge or discharge for like an anode material. I'm either adding lithium ions to the carbon or I'm taking lithium ions away from the carbon. And one of those is a charge and one of those is a discharge. In this case, it's like I'm setting up negative ions at the surface or I'm setting up positive ions at the surface. Either way, I'm setting up a capacitor. Kind of doesn't, feels like it doesn't matter which one. So either of them could be the charge or the discharge. Like the charge is setting up of ions, whether they're positive or negative. The discharge is releasing that capacitive. Something like that. I don't know. Maybe that's not right.
In a way, we think about capacitors, especially electrical double layer capacitors, as being able to flip polarities just like that, where positive or negative charge could reside on the metal, and then the counter ion, takes on the other side of the charge. And so we think of it that way. But for batteries,
that's not how it works.
It doesn't work that same way.
So correct me if I'm wrong, but if you have a capacitor that has stored charge, and you extract that stored charge, then you no longer have the buildup of the charge at the surface. You've used it, like you've discharged a capacitor. So it's like you had a positive charge over here and a negative charge over here, or vice versa. And you want to like use that energy to like start your car or do whatever. Then when you've used that up, there's no now they're like two neutral plates. There's no charge. There's no difference in charge. It's built up, right?
Yeah, if you discharge them all the way to like zero.
Yeah, right. Yeah, exactly. Okay. Yeah. But my point is like whether this one was positive and this one was negative, or this one was negative and this one was positive, I still have energy to get out of that. Maybe that affects the direction.
And it's just you would say the directionality. Yeah, the directionality would then play a role, because if it's one side or another, then you have either a positive or a negative.
Right. So the direction that it would flow
with respect to other things.
Yeah.
That's
so
right.
What's not clear to me is whether you like if you have a supercapacitor that has carbon on both sides.
Yes.
You're going to charge it up in a way so that whether this one's negative and this one's positive or vice versa, when I discharge it and I make them both neutral, I get current that flows this direction because that's the direction that runs my thing.
Yeah.
But it could be charged either way. Like there's nothing that keeps you from charging it either way, like intrinsically about the material.
Yeah. In that case, there's nothing intrinsic about the material.
So this is why the answer is it's hard to answer, because with a battery, there is something that makes it hard. Like if I have just plain carbon, I can't take more lithium out of it. I can only put lithium into it. It goes one direction or the other very clearly, right? It's like it's more easily defined with a battery electrode. Like it has to which direction it goes, one or the other, and which one is the charge and the discharge. So
and in Cigar's situation, which we don't have any details on, he may be working with an electrolyte where, and this is something that happens, like it's a lot easier for metals to hold positive charge just naturally. Like negative, like I remember our other colleague Lee, who's super smart and stuff, occasionally you can have negative anions just stick to a metal just because metals naturally lose their electrons. They naturally have positive charge. It's intrinsically easier. But that's not to say you can't bias an electrode negatively. That absolutely can happen. But the structure of the surface can always be a little bit different. So Cigar may be working with a strange electrolyte where, like, he has, he may have like a, I don't know, iron 2 plus and chloride 1 minus. So he's got twice as much chloride negative charge out and only a single iron 2 plus, but the ionic strength is different of those two guys, anions and cations. So maybe in certain situations with what he's working on, there is it's not a situation where you could charge it and then discharge it and they're exactly equal and opposite.
Hmm.
But we don't know that detail, right? That's
Yeah.
that's like a cigar thing he has to kind of think about or figure out.
Well, I think we've talked through this a good amount.
Yeah.
We'll leave it there. But yeah, anyway, I hope that's kind of maybe something in
Yeah,
there
helps a little
clarifies
bit.
it for you a little. I guess it's I do find generally that that kind of terminology isn't exactly the same
Yeah.
or analogous between batteries and supercapacitors. But I mean, that plot that I just showed you, for instance, like it's sort of like wherever you start from and go to is the charge. Sort of seems to be my impression. So in this case, if you start at -1 and just go to 0, and you get that curve, whatever rate you go, then you plot that over time. That's the charge, and then you go back, and that's the discharge. That seems to be what it is most
Yeah.
most likely answer, I guess. But let's move on from there
Yeah.
and try to finish these last couple of questions. Oh, sorry,
Yeah. I
we
think
both.
there's just two more questions.
Yeah. So Uma has a question. I think we both hitting it. There you go.
Yeah, we
Okay.
did both at the same time.
It's like unlocking the car door at the same time you're trying to open it.
Yeah.
So I read about estimating the amount of metal deposited on metal nanoparticle modified electrodes, and the authors mentioned that they opted out of silver chloride and chose copper sulfate. Why? My guess is that they wanted to avoid chloride contamination. Would be my guess. Obviously, I'd have to look at the paper. Maybe you're asking
Or
because
silver
maybe
contamination.
yeah, it could be silver
Yeah.
contamination. I'm not sure if they explained why or they just said they opted out. One of the things, yeah, perhaps silver. There's some. I mean, it's the reference electrode, so in theory, it shouldn't obviously interact. Directly. The reference electrode's connected in the potentiostat through an electrometer with a very high impedance, and so it's not taking part in the reaction other than just being a stable reference point. But if there's worry, especially with nanoparticles and measuring very small sensitive concentrations, and they might be worried about silver somehow coming in contact, maybe that's it. But it could be also a chloride thing. Chloride, for instance, can be uh, sticky and clog up electroactive sites. In bulk normal situations, a lot of times this isn't that big of a deal, but I guess if you're measuring nanoparticle whatever, and that one nanoparticle has a chloride ion kind of bugging on it or something, maybe that they're trying to avoid that. Sulfate is probably less likely to be invasive, maybe, or maybe they're doing it in acid and sulfate is there because they have sulfuric acid, something like that. My guess is it has to do with the chloride. If you have a silver chloride reference electrode, even if you don't have chloride in the main solution, you'll get a little bit of like diffusion of chloride through the reference electrode FRID, and you might get some few ions of chloride in your main solution over time. And if you're trying to make really sensitive measurements and you just can't deal with um, an anion that might absorb a little to the surface, you probably do away with the chloride. But that's just my guess.
Yeah. Yeah. Be anything. But yeah, most likely it.
So anyway, yeah, that'd be
All
my
right.
guess. But the last question from Vertigo.
Yeah. Vertigo asks, I'm using Metrohm Autolab with 3 electrode heck.
Photoelectrochemical cell?
Yeah, I'm assuming.
Yes.
Oh, photoelectrochemical cell.
I don't know. I guess that's maybe what PEC means. So
Yeah. But it has 5 wires with WE, S, ground, CE, and RE. But the things is my EIS didn't show up. Can you tell me which of those cables connect with each electrode? Well, um, I would say you probably I would talk to Metrohm specifically about because they're colored differently. They probably mean different things. It's probably also in the Autolab user guide as well, just to double check and confirm. As an initial guess, I would say WE is probably working electrode. S might be the sense line for the working electrode.
I think that's correct. If I remember, I used a Metrohm in graduate school. I
You
think
use the
that's
Metrohm?
correct. So you're going to want to plug the S into the WE.
Yeah, so you want S and WE connected together. Ground can probably be disconnected for now. You can also ground that to the instrument or to another piece of equipment. You know, it's just to minimize electrical noise. CE is counter electrode and RE is the reference electrode. But if you have a 3-electrode setup, then WE and S need to be shorted together to the working electrode. CE needs to be connected to the counter electrode, and RE needs to be connected to the reference electrode. And Uma had a comment for you, which was if you were doing a 2-electrode system, you would need to short the counter to the reference. But it doesn't sound like you have a 2-electrode system. With a 3-electrode system, your working and sense lines need to be connected, but the counter and reference are separated to the respective counter and reference electrodes. So try that, and then I think the EIS should show up.
Yeah. All right. I think we've reached the end. I think we're about there now. So, all right. Well, we're gonna call it there for the day. And again, I guess like you said at the beginning, thank you everybody who came by our booth in San Diego this week. I guess it was this week. That's why we're so jet lagged.
Yeah, that's right.
And so anyway, it was great to meet some people at the booth who have watched our content on YouTube and I guess our videos and our live streams and everything. Very much appreciated. Yeah, well, thank you very much. I guess everybody, I suppose it's just a regular week here. So next week we'll be back with you for another episode, and we're quickly approaching episode 100, which can be very exciting. And I should not make any crazy promises because I doubt we'll do anything special, but it will be episode 100.
Yeah.
In my head, I was like, we were going to do a crazy thing, and it's like, no, we're not. We're not going to do anything.
Yeah.
I mean, maybe we will.
Maybe.
You know, I don't know. You stay tuned. Just wait and see. But in any case, thank you again, everybody, and we'll see you next time.